In this video we're going to talk a bit more about the forced damped oscillator, specifically about the phase angle phi. We've seen before that this phase angle can be given by this expression here, the arctangent, and it depends on the damping factor and the frequency ratio. We've seen in the previous video that the time response is given by this expression, but we can also calculate it by a numerical solution using ODE 45, built in MATLAB and octave. So similarly to the previous video, I'm calculating the time response using a numerical solution, specifically using ODE 45. And for that I pass all the parameters of the system, specifically here the value of the excitation frequency omega. For the frequency response, now I'm using the phase angle phi here, given by this expression, which is this expression here. Just note that I'm using the a tan 2 function to calculate the phase angle. I'm also calculating the current phase angle related to the current excitation frequency omega. Regarding the figures, on the time response, so the first subplot, I'm superimposing the force as function of time to the displacement as function of time. Regarding the other subplot in the frequency response, I'm plotting the phase angle phi as function of the frequency ratio and superimposing the current phase angle as a red dot. For the interactive part, as I update omega, I update the value of the current phase angle phi1 here, and also I recalculate the time response. And then I update the time response, the force, and the current phase angle data in the figures, in the respective figures. So I do that for increasing omega and decreasing omega, as we've done before. So go ahead and make sure your script has all these changes. And if we go ahead and run this, we'll see this figure here showing the time response here in black, the force as function of time here in red, the phase angle as function of the frequency ratio here, and the current value of the phase angle as shown here by the dot. So if we look here in the time response, we can see that the displacement as function of time, when we get here into the steady state regime, the peaks on this displacement curve, they're not exactly in phase, or they don't happen exactly the same time as the peak in the force. So if we zoom out a bit this response, you can see that the peak on the displacement is a bit further forward on time regarding the peak and the force, which is here in red. So this difference from where the peaks on the displacement and the force are is exactly the phase angle. And it's called an angle because these two curves are harmonics. So if you look here into the expression for the force, which is the cosine of omega t, this argument here of the cosine can be seen as an angle. So this difference in where these peaks occur can also be shown to be an angle, and that's the phase angle. the difference between where the peak and the displacement and the peak and the frequency and the force occur. So what this curve here is telling us is that this frequency, this phase angle phi, changes as we change the forcing frequency. So if we go ahead and go increasing this phase angle, this forcing frequency, we see this red dot moving over this curve. And if we look here into the time response, depending on your screen, you might need to zoom in a bit to see what is going on. And we see that as we keep increasing this frequency, excitation frequency, obviously we have changes in the amplitudes, but we are more interested here in what is going on between this difference, and we see that this difference between where the peaks occur keeps getting bigger. The displacement peak keeps going forward and forward as in relation to the peak and the force as function of time here. And this is what this curve is telling us, that as we keep increasing the frequency, the phase angle increases as well. And it keeps going on and on to the point where we can have the forcing the peak and the force and the peak and the displacement completely in opposite phases. So this value here is exactly pi. So for very large frequencies, the displacement peak occurs where the force is at a minimum value and not at a maximum value. So maybe if we have a better zoom in here, the peak and the displacement here is occurring almost exactly where the force is in a valley here, so in the minimum value of the force, as opposed to what happens in low frequencies where the peak and the displacement will be very close in time to the peak in the force, which you can show in here. So that's what the phase angle means to us. If it's if it's a small phase angle, we have the peaks occurring almost at the same time. And if it is a very high frequency where the phase angle is close to pi, we see that the peaks are at opposite phases, meaning the displacement, the maximum displacement, happens close to the minimum value of the force.